All right, so let's recap. Yesterday you had a quiz over chapter 9. What were we doing in chapter 9? Should be kind of fresh on our minds. Okay, we're trying to make a guess about either a population proportion or mean. Couldn't have said it better myself. Think about that for a second. We're trying to make a guess about something we will never know. And we're trying to say, I think it's in between whether it is a mean or a mean or a proportion. I'm trying to say, I think it's between these two values. And we want those two values to be as close together as we can get them. So our margin of error is small. But we want to be reasonably confident about that. That's what a confidence interval is. We're making a guess about a population parameter. We'll never know what that parameter truly is. We're just making a guess. It could be the average height of 18-year-old girls in Texas. That number exists for any instant of time, but we'll never know what it is. Because tomorrow will change. An hour from now it might change. 3 minutes from now it might change. But if you could freeze time for a second, that number does exist. And we can make a guess about it by doing sampling. Okay, that's chapter 9. We're making a guess. Chapter 10 turns it around and says, somebody's telling us what they think the population average or the population proportion is. And we're going to do a test to see if we believe them. It turns it around. So if I said the average height of 18-year-old girls in Texas is 5'4", then what chapter 10 is going to do is say, let's do some samples and see if we believe you. We're not making a guess anymore. We're trying to prove something's wrong. We're testing that. So that's what hypothesis testing is. There's some claim, some statement about the population. Now it's either going to be, for our purposes, it's either going to be an average or a proportion. Now how are we going to do that? Well, we need a couple of things. We've got to get samples. Stats is based on samples. And we've got to think in terms of probability. Those two things together are going to let us make a hypothesis test. Oh, the dealer told me this car was very reliable. Trouble is, every other day it won't start. The reality doesn't match the claim. And that's what we're going to try and figure out. Do we believe that original statement or not? Now, this little thing right here is in the book, but it's also in your notes. How are we going to do that? Well, we take a statement about the population. Again, for our purposes in here, it could be an average, it could be a proportion. There are other things we could do this with, but we're not going to get into that in this class. Then we get samples. And then, in light of probability, we're going to say, how likely was it that our sample said this when the claim was this? And if you think about it, for hundreds, if not thousands of years, people knew that the sun went around the earth. Why? Because you can see it. Stand outside. Watch that thing go over the earth, over your head. That's what sundials work. How long did it take to convince people otherwise? Some people got in trouble for trying to do that. All right, so that's kind of the basis of what we're doing. We take a claim. We're going to try and use evidence and probability to disprove that claim. Here's an example. There's this store called Candy R Us. right? All it's got in there is candy. Thousands of Snickers bars. And that store tells us that 97% of their Snickers bars have been on the shelf for less than a month. That's a claim they're making. And we kind of think, no, I think it's less than 97%. So we're guessing about a percentage or a proportion here. Their claim is 97%. Ours is less than 97%. So what do? We get a sample of 50 Snickers bars. Random sample. Wait a minute. If we're getting a sample, does that mean that the sample size has to be 5% or less of the population size? Yeah, all that's still true. This is the third chapter we're seeing those kind of rules. Does it mean that it has to be random? Yep. This is a proportion or a percentage. So does that mean that NP times 1 minus P has to be greater than or equal to 10? Yeah. Otherwise, we don't have a valid test. So I get my sample, and here's how it works out. 44 out of those 50 Snickers bars were on the shelf more than a month. I'm sorry, less than a month. So 88% were actually on the shelf less than a month. Now, on the surface, does that seem to disprove what the store is saying? Maybe, maybe not. This was a random sample. Is it possible that we just found enough older ones that this came out the way it did, just by chance? Let's assume the store is telling the truth. Could we get a result like this just by chance? Sure. Then how are we going to know? Am I going to accuse the store of lying when really they might not be? Or am I going to go, I think the store's cheating people? You better be sure about something like that. Like I just said, you've got to decide. If we assume what the store is saying is true, how likely are we to get a sample like this? And that how likely are we is where probability comes in. So those rules of probability start kicking in big time here. He tells me he loves me. But I see him walking to class with the same blonde chick every day. It's not me. He says they're just friends. He's a good guy. Then I saw him carrying her books. He's a good guy, so that kind of goes along with his personality. I saw him touching hands in the hall the other day. Now, at some point, if I'm a girl, I'm going to think, he's claiming he loves me, but the evidence doesn't match up to what his actions are. And that's all we're doing here, y'all. Do what? Yes, yes. If you see red flags, believe them. If somebody tells you who they are, listen to them. A lot of times they'll tell you exactly what kind of snake they are. Okay, now think about the thought process I went through in that silly little example. What's the claim? He loves her. If I take you at your word and you love me, then why am I seeing evidence to the contrary? And that's all hypothesis testing is. That's it, in a nutshell. Do we have enough proof yet that the store's wrong? Or assuming that what the store is saying is true, could we get results like this? Yeah. Maybe. And that's where we start doing hypothesis testing. Now, in this section, we're not going to actually do a hypothesis test. So how are we going to decide this question right here? We're going to do a hypothesis test. We're not going to do one in section 10.1. So, some vocabulary. The store's claim of 97% is called the null hypothesis. The null hypothesis. And it's got a little symbol, H sub 0. And that word null comes from the 0 part. So this is our original claim. The sun goes around the earth. He loves me. 97% of our Snickers bars are on the shelf for less than a month. Those are all null hypotheses. That's where we're starting. Our claim, our counterclaim, if you will, in this case, is called the alternative hypothesis. And it's abbreviated H sub 1. If you take stats later on, if you wanted to take more stats, a lot of books will say H sub A for alternative. It means the same thing. So we've got two hypotheses that are competing here. So our alternative hypothesis is, no, we think less than 97% of your Snickers bars are on the shelf for less than a month. Then this is in your book. Thank you so much. There's three ways we can set these things up. Notice, we can say the parameter about the population here, our null, is that it equals something. It equals a value. The average height of 18-year-old girls in Texas is 5'4". We'd say mu equals 5'4" right there. The alternative might be, no, we think it's something different. Now think about that. That means it could be either higher or lower. That's called a two-tail test. Or we could say the null is our parameter is some value. Now notice the parameter always has an equal by it for the null hypothesis. The null is always, it equals this, it equals this, it equals this. We could say, no, we think rather than what you're saying, the real population parameter is less than that. That's a left tail test. A right tail test is just the opposite. No, we think the real population parameter is more than what you're claiming. Hey, drug manufacturer, you claim that this treatment that you've got will only kill 2 people out of 100,000. We think it's more than that. That might not be acceptable to us. And like this points out in your notes, in our little Snickers example, it's like the second one here. It's a left tail test because we think that the percentage of Snickers on the shelf for less than a month is really less than 97%. All right, so on this little thing right here, we're going to say, well, what are the null and alternative hypotheses? And then let's see whether it's a one-tail or two-tail. So we have a pharmaceutical company that's developed a new antibiotic. And we know from experience being in this field that our competitor's drug that treats the same thing, 2% of the kids taking it have headaches as a side effect. The FDA wants to know if our drug, our new antibiotic, causes more than 2% headaches. Real world? Yeah. So our null hypothesis would be, oh, by the way, you have to decide whether you're talking about a proportion or an average, just like the last couple of chapters. Our null would be what? We claim our medicine doesn't cause any more headaches than everybody else. So P notice I'm using P because we're talking about a proportion here, is 2%. We're talking about our population here, our drugs. 2%, just like everybody else, headaches. The alternative would be what? More than 2%. That's what the FDA is interested in. Yeah, your drug might work, but does it have worse side effects than everybody else's? In which case we might not approve it. One tail or two tail? One, is it left or right? Yes. So you can make a silly little drawing like this, and this is where they get the idea of the tails. I'm putting 2% dead center. This is normal distribution. And we're saying, yeah, here's your claim right here in the middle, that 2%, but we think the real proportion of headaches that you cause is out here on the right, more than 2%. So it's one tail, it's a right tail test. Okay, if you've ever looked at Kelley Blue Book, they give you prices of all sorts of vehicles in there. And in this Blue Book, they said the average cost of a 3-year-old Chevy Corvette is $59,000 something. Grant, inquisitive soul that he is, he wants to know if really the average is different from that. Well, different can mean higher or lower. So we're talking about an average here. So what would our no be? That no, the average really is this, just like Kelley Blue Book said. We're really talking about an average of a little over $59,000. This example is several years old, so it's a lot more than that now. What's the alternative? That no, it's different. So it's not equal to that. It could be higher, it could be lower. We just think it's different. So we're going to do a hypothesis test. One tail or two? Silly drawing. There's the middle. It could be out there on the fringes on either side. Making sense so far? We're just getting vocabulary today. That's all we're really doing. Just getting the basic idea of how does a hypothesis test work. Yes, sir? If it says different, look at the way the thing's worded. That's a good question. If it says different, it means not equal to what they were claiming. Like up here on our first one, what's the alternative hypothesis? More than 2%. Different means it could be more or it could be less. When would that matter? When would you ever want just different? That doesn't seem so useful. If I'm manufacturing these markers, right? I've got the caps, and those caps have to be within a certain tolerance, right? If the diameter of the cap right here is too big, what's going to happen? I go like this, and the cap's going to fly off. If the diameter of the cap is too small, what's going to happen? Won't fit the marker. So then I might be interested in, is that cap too big or too small? It becomes like a Goldilocks thing. I want it in the tolerance there. I want it to be within a certain tolerance, plus or minus. These come in handy. All right, two-tail test. When we're doing these hypothesis tests, there are only 4 ways they can turn out, just 4 outcomes. Let's go through them. We're either going to reject the no or we're not going to reject the no. Those are our 2 choices. So number 1, The alternative hypothesis is true. That means the null is not true, and we reject it. Though that's a good choice. That's a good decision. Number 2, the null hypothesis is true, and we don't reject it. Well, there's another good call. So those first 2, we make the right decision. One when the null is not true, and one when the null is true. Number 3, the null is true, but we reject it. We passed right by the correct answer. That's called a type 1 error, when the null is true and we reject it. Number 4, the null is not true, but we don't reject it. So we don't catch the fact that the null is not true. Now, all of this is based on our sample. So once we do our sample, we're making these decisions based on the outcome and the rules of probability. And so this little chart will help you remember it right here. Along the top, we've got the reality of the situation. The car is really a junker. And on the left, we've got your conclusion based on your testing. Remember, stats is making your best guess with what you know. These kinds of decisions come up in business, in manufacturing, in education, in medicine, in just about any field you can think of. That's why a whole lot of degrees in college are requiring people to take statistics. Let's look at this. So pretend like we're the board of directors for Medco. We've got this antibiotic, and we know from experience that kids taking a similar antibiotic from other companies, 2% of those kids have headaches as a side effect. So the FDA wants to know, is ours worse than that in terms of side effects? So look at the null. P, we are talking about a proportion here, is 0.02. What's that saying? The claim from Medco is, no, our antibiotics don't cause any more headaches than anybody else. That P is talking about Medco's products. No worse than anybody else. The alternative is, no, it causes more headaches. So type 1 error is the null is true and we reject it. So in reality, our medicine doesn't cause a higher percentage of headaches in kids. But the FDA doesn't believe that. What's the result? If we're Medco, we might go, well, maybe we shouldn't develop this at all. Or if we're the FDA, we might say, we're not going to approve your drug. And all that research you did costing you millions of dollars is out the window. These things have real world ramifications. Some of them are pretty bad. So that would be a type 1 error. A type 2 error would be saying, no, our drug really does cause a higher percentage of headaches. But the FDA goes, no, you're fine. So the null is false, but we don't reject it. Now then, the pattern is you either reject the null or you don't. That's what it comes down to. That's the conclusion. You either go, I'm going to reject the idea the sun goes around the earth. Or I don't reject it. We never accept the null. We never say, therefore the null is true. That's not part of this. We either reject it or we don't. All right, what's the result? Well, one of them is we spend a lot more money and we produce this drug, and then it gets out in the marketplace, and average people and doctors are going, boy, the headache rate for this drug is horrible. So doctors don't prescribe it anymore. We spent all that money. People have, gone through the pain of more headaches. We're talking about kids here. That would be a type 2 error. Now, you might be getting the impression sometimes a type 1 error is worse. Sometimes a type 2 error is. And you have to keep that in mind. Sometimes maybe a type 1 error would cause a catastrophe. Sometimes a type 2 error would. Sometimes both of them do, and you have to decide which is the less evil. Real life. All right, so you have to put things in context. You have to say, in the context of this scenario, what am I looking at here for a type 1 and type 2? Terminology. The level of significance is called alpha. Where have we seen that before? Well, with confidence intervals, those critical values, one of them was Z, and then its subscript was alpha divided by 2. They're talking about this alpha right here. And for averages, it was T, alpha divided by 2. This alpha. It's called the... What did just mess up the whole momentum of everything, Katie? Okay, so the level of significance gets important. It's the probability of making a type 1 error. File that away. And along with that, we have beta, which is the probability of a type 2 error. So alpha, also known as the level of significance, that's the probability of making a type 1 error. Beta is the probability of a type 2 error. Okay, looking at this, you choose alpha before you ever take a sample. You choose ahead of time, how low do I want the probability of a type 1 error to be? That's pretty cool. That's sort of like a confidence interval where you have, I want the margin of error to be between 1 and 2%. You choose that ahead of time. So we get to choose alpha. I can say I want alpha to be 0.01, or I want alpha to be 0.05, or I want alpha to be 0.1. Here's the thing. As you make alpha lower and lower and lower, beta comes up. So if you're saying, I want to make the probability of a type 1 error really low, then what are you doing? You're increasing the probability of a type 2 error. And that means you have to decide, you, the investigator, have to decide, well, based on my results, which one's going to be worse? If we're talking about airplane inspections, and a type 1 error is checking that airplane too much. It costs money. We're going to do a super thorough investigation of that airplane. And a type 2 error would be what? It crashes. As the probability of a type 1 error goes down, the probability of a type 2 error goes up. And so of those two things, I'd rather over-inspect a plane than under-inspect one because of the catastrophe caused by a type 2 error there. Okay, a couple of problems here. On these, we want to know what the null and alternative hypothesis are. And then kind of look at a type 1 and type 2 error a little bit. So for this first one, I didn't realize this. Federal law requires that if you're manufacturing peanut butter and you say there's 32 ounces of peanut butter in my jar, you better have at least 32 ounces. So this company says, yeah, that's what we got, 32 ounces. That's the null hypothesis. Okay, we're going to assume, let's take them at their word, 32 ounces. In words, that means what? They're telling the truth. They're not gypping anybody. This consumer advocate, though, feels like, yeah, that's what you say. So the alternative hypothesis is, I think you're putting less than 32 ounces in there. So this is a left tail test because it's less than. And that means they are gypping people. Okay, we have our two hypotheses. Again, we're not actually doing a test that starts in section 10.2. Type 1 error. The manufacturer's telling the truth. But we don't believe him. He's doing everything right. And our testing indicates he's not. So we don't believe him. Any ramifications? Well, yeah. Our consumer group could sue them. We could start spreading the word that this brand of peanut butter is gypping you, which means they could sue us for giving them a bad name. Their company could go out of business. Oh, yeah, isn't that the peanut butter company that gyps people? It's a type 1 error. The null is true, and we reject it. Type 2. The manufacturer is cheating. But our testing doesn't catch it. Any ramifications? They are cheating. We don't catch it. People get cheated. The manufacturer makes profits that they shouldn't. Which is worse in this case, type 1 or type 2? I would go with 1. You're falsely accusing somebody. By the way, does stuff like this happen in criminal trials? Yeah. A criminal trial is a hypothesis test. More about that later. Okay, here's one. The proportion of students earning a bachelor's degree within 6 years, now think about that, a 4-year degree in 6 years, was 0.236. So we're talking about a proportion. Now, the president of Joliet Junior College says, no, I think our completion rate is higher. So the null is no, Joliet Junior College, their completion rate is the same. In other words, they don't have a higher completion rate. Now notice the P we're talking about here is the Joliet students. That's our population of interest. The alternative is going to be, yeah, they really do have a higher completion rate. Again, Not the world in general, but these people at Joliet. Type 1 error. The null is true, but we reject it. What's the result? Well, the college could advertise, hey, come to Joliet, you're going to graduate faster than you normally would. Colleges are businesses, they're competing for your business. After they do that, then people go, wait a minute, that's not really true. Joliet's lying to us. You don't get out any faster at Joliet than you do anyplace else. Type 2. The null is false, but we don't reject it. Meaning what? They really do have a faster completion rate. We just don't realize that. Based on our test, based on our sample. Result? Well, you might not go to Joliet thinking that they're no different in terms of how fast you get out. Or the people that are at Joliet, their board of directors might go, well, if that's true, then we need to revise our thinking on this and change up degree plans and things like that. I'll leave it to you to decide which one would be worse there, type 1 or type 2. I think we got one more. Okay, according to the CDC, 19.6% of kids aged 6 to 11 are overweight. But the school nurse says, no, I think at our school it's different. When they throw the word different in there, you know right away they're talking about a two-tailed test. So our null would be, yeah, at our school. Now, this P is the percentage at our school where the nurse is. The null is, yeah, we're no different from anyone else when it comes to the percentage of overweight kids. So we're no different from the population. The alternative is, yeah, we're different. And notice that's a not equal to there. It's a two-tailed test, meaning we could have a higher percentage of overweight kids or we could have a lower percentage of overweight kids. It's just different. But we're not the same as the population in general. Something's different at our school that might warrant further investigation. So type 1 error is the null is true. Our school's no different. But we think it is. Population obesity a problem in this country? Oh yeah. Oh yeah. Ramifications of this. We do reject the null even though it's true. We might say, hey, we're doing okay. Whatever we're feeding these kids at lunch, that's good. We don't need special programs for them, either underweight or overweight. Type 2. The null really is false. This school is different. Ramifications. So what if the kids at our school, their weight is perfectly healthy, but these tests come back and say, no, they're overweight? We might start feeding them kale for lunch or something drastic, to get their weight down. What a torture. Or what if our kids have a higher percentage of obesity? We might go, hey, keep that pizza coming. It's not hurting anything. So there, in a nutshell, is what we're going to be doing in the next two sections. We're going to be doing actual hypothesis tests. But this gets you to thinking, okay, here's the framework we're going to be working in. And we'll pick up there next week. All right, thank y'all.